All right. Thank you, Chris. And welcome everybody from around the world for this exciting panel discussion on entry, descent, and landing, or EDL. I'm Tim Cichan. I'm the Space Exploration Architect at Lockheed Martin, and I'm responsible for leading teams that develop Moon and Mars exploration architecture concepts. Before my current position, I actually spent about a decade on the Orion program and a variety of different roles. And then I started my career on commercial communication satellites. So let me introduce the panel. Here we've got Michelle Munk, who's on detail to NASA headquarters. And she's the system capability lead for entry, descent, and landing. Adam Steltzer from JPL, he's the chief engineer of Mars 2020. And Ashley Korzun from National Langley, she's the deputy principal investigator for entry systems and for Plume surface interaction. So 3 great experts. I'm pretty excited. So today we're going to learn about NASA's plans for developing EDL technology for crewed missions and the history of robotic entry, descent, and landing, including, of course, about learning about Mars 2020 on its way to Mars now. And I really want to hear about, what's left to be done to land crew on Mars. What are those challenges? And also to hear about everything we already know from all of these great robotic missions. And if you could bring up my chart. All right, thanks. So Lockheed Martin has a long history as NASA's partner on Mars mission, going all the way back to Viking in the mid-70s. Martin Marietta designed and built the Viking landers. We're the only company to have already landed on Mars 4 times. And so we've got a variety of different roles across the years, sometimes designing and building the Mars Aeroshells, which we've done for every NASA mission, and then Mars orbiters, but also spacecraft going to other planets and locations, as well as sample return. So we've done missions to sample the solar wind, to sample comet dust, and brought those samples back to Earth. So Earth entry, descent, and landing. And of course, the OSIRIS-REx mission is at asteroid Bennu right now. I'm going to take a sample here in October and bring it back to Earth in 2023. And we are taking all of this experience and everything we've learned and putting that into development of crewed entry, descent, and landing. It's a picture there of Orion's flight tests from 2014. Of course, Orion's going to return from the moon and maybe Mars one day. And then the lower left is an image from our Mars Base Camp concept, and it's a single stage crewed lander. But let's get going. We can take down that slide. And so as we go to different panelists, I'd like to ask you to also, tell us a little bit more about what your role is and what your background is. I'm sure folks are interested. And on the way we'll do this, we're going to hear from Michelle and Adam and Ashley. I'll ask a few questions after their presentation, and then we'll have a group Q&A where I'll ask some of my own questions and I'll look at the audience questions. So Michelle, thank you for being here.
Thank you for having me, Tim, and the Humans to Mars Summit. I'm really excited about this afternoon's panel. I am currently, as Tim said, the Entry, Descent, and Landing Capability Lead for NASA, and I work for the Space Technology Mission Directorate. I started my career 32 years ago as a co-op at Johnson Space Center, and since then I've also worked at Marshall Space Flight Center. I am usually physically at Langley Research Center, and I'm on detail to NASA headquarters. I have done a variety of things, but I actually started my career as an interplanetary trajectory analyst for human Mars missions and human lunar missions. So that's been a constant. But through the years, I got into more of the atmospheric part of the flight and the technologies that we were going to need to accomplish the architectures I've delivered flight hardware to the space station and also for instrumenting the heat shield, first of Mars Science Laboratory, and most recently we instrumented the heat shield of Mars 2020 as well. So it's great that we're learning from every flight that goes now in terms of our entry, descent, and landing performance. So if I could have my first slide, I'll get into the presentation. So next slide, please. So this chart is kind of a little history lesson in what we've done so far at Mars that Tim alluded to, and Adam will tell you about our current mission. But just to give you a little context about how our vehicles have looked thus far and what we're facing as we look to the future and landing humans on the red planet. We're going to need new approaches to entry, descent, and landing when we start talking about humans and all the things that they need to live and conduct work successfully on the surface. Payloads of about 20 metric tons, whereas we've only landed 1 metric ton with the Curiosity rover thus far. So we have quite a large leap in scale, both mass and size. We want to be able to land our humans and their cargo precisely relative to each other to make the most of their surface operations. And so we really have to employ some new capabilities. We won't be able to use heritage capsules like we have in the past, as you see from Viking through Mars 2020 there in the middle of the chart, because those are limited by the launch vehicle shroud size. When we're putting 20 tons behind a heat shield and trying to slow down in the thin Mars atmosphere, we're going to need something much bigger than the diameter of a launch shroud. We're looking at inflatable concepts, and you've seen some of the other concepts, both probably from Elon Musk earlier in the week and on Tim's chart. There are different approaches to trying to land these larger payloads, some all propulsive and some relying more on atmospheric deceleration. And speaking of atmospheric deceleration, we can't use parachutes for these large payloads either, because they would have to be too large and they just become untenable. So as you see on our historical missions on the chart, we've used parachute descents for every mission since Viking in the supersonic speed regime. And then we've employed different ways of terminal descent, either retropropulsion or airbags for Pathfinder and the MER missions, and also some pallet scale landers. So we've used some different things for terminal descent, but those parachutes have been a constant that we won't be able to rely on in the future. We'll need to use retropropulsion at a higher altitude and velocity than we have just for our soft landings. And Ashley is going to tell you much more about that. So let's go to the next slide. Here is what we call our concept of operations for human class Mars EDL, and this one in particular shows you the inflatable decelerator called the HIAD, the Hypersonic Inflatable Aerodynamic Decelerator, and it's followed by a period of supersonic retropropulsion all the way down to the ground. So what makes this vehicle viable for a 20-ton payload is that it fits in the launch shroud. It flies to Mars with the heat shield basically stowed in front of the vehicle. When it gets close, there in the upper right-hand part of the screen, it deploys to 16 or 18 meters in diameter, and then forms the rigid heat shield with a flexible thermal protection system to protect us against the heating and loading as we come into the atmosphere. As we come down in velocity and we kind of run out of the atmosphere, we turn on our engines, and we'll be turning those on somewhere between Mach 2 and 3. So 2 and 3 times the speed of sound, much higher than we've done in the past, at an altitude of about 8 kilometers. And so we'll be going almost horizontal still at that point, and then we'll land softly on the ground, stick a pinpoint landing, and with advanced terrain relative navigation and other systems. And then we'll retract the heat shield so that it's not in the way of the astronauts performing their mission, and we'll start surface operations. So from the architectural approaches that we've been studying thus far within NASA, this is really the only solution that we've found that closes the architecture mass-wise and fits in the SLS 8.4 meter shroud. We've looked at other concepts such as rigid middle over D vehicles or deployable mechanical vehicles, but they either have insufficient volume or they're too massive. So unless our architectural approach changes dramatically, we think this is the most flexible and robust solution that we've been able to think of. However, we've got quite a bit of time before we are going to implement this mission, and so we invite other ideas and other approaches. So next slide. When we talk about how to get from where we are today into that ConOps that I just showed you and the scale of vehicles that we're talking about, we've put together a notional development timeline, and you'll notice that I've put it just relative to the endpoint of putting the humans on Mars up there in the upper right with the green star. And I noticed that the title of this panel, or we're within the long poles section of the workshop. And so EDL has been called the longest of the long poles for getting humans to Mars, because it's going to take us 15 years or so to really mature all of these technologies to the point where we feel comfortable flying these large-scale missions. We do have a significant item on the manifest right now that's called the Lofted flight test, and that's the low Earth orbit flight test of an inflatable decelerator. And this is a 6-meter version of the HIAD that I mentioned. We'll be flying it in 2022 at Mars-relevant heating conditions to validate that construction. So we're very excited about that. That's being funded within the Space Technology Mission Directorate, and it's a partnership with United Launch Alliance. We are going to need some large-scale flight tests that are guided, fully guided, and have full GNC like we'll need at Mars. We also need to work on obviously scaling these systems up to the large diameters that we need. And we're going to have to do a lot of testing of the retropropulsion system, along with precision landing, understanding the interaction of the engine plume with the surface, or plume surface interaction, PSI. And then all of these developments are really reliant on end-to-end simulation capabilities. You'll notice that many of our subsystems are being tested at Earth, but we cannot effectively test the entire EDL sequence in the vicinity of Earth. And so we need to rely on highly efficient computational models that are validated to actually do these designs. So all of that work will feed into development of those cargo missions and eventual human missions. So next slide, please. So I think just to summarize, we are currently maturing technologies to address the challenges of Mars EDL, and we're heavily leveraging lunar exploration where we can. In particular, the precision landing and hazard avoidance technologies and the plume surface interaction modeling and methodologies are really being developed for use in the Artemis moon missions, and those will feed forward to Mars. I talked about the HIAD and retropropulsion, and Ashley's going to tell you more details about those developments. We are applying our methodologies in system level performance and simulation to the Artemis missions and then to the flight tests that I mentioned. And this is all anchored in advanced modeling and computation. Within space technology, we leverage multiple programs and partnerships with industry and academia. So we have a very vibrant community, many partnerships going on with industry as well as universities. We have a whole thrust area within space technology that is dedicated to entry, descent, and landing. So we're very fortunate to have strong support within the agency. And I didn't get a chance to talk too much about it, but the commercial lunar landers, the CLIPS missions, are a key component of our technology demonstration, particularly, as I said, for precision landing and plume surface interaction measurements and demonstrations. But we can't forget that the robotic Mars science missions that we've been flying are giving us all great experiences, and those will be paired with these focused technology development efforts to pave the entire way for landing humans on Mars. And so with that, I'll end and take any questions.
All right, thanks, Michelle. So one follow-up question, that chart with the timelines of humans on Mars was great, but it doesn't have years, so I wanted to check, where roughly are we right now on that chart, and therefore what's the next new start? You mentioned the high altitude flight test at Earth, but is there another new start coming up?
You'll see the aggressive nature of that that timeline chart kind of shows that we're doing lots of things in parallel. So we do need to get lots of things started. But as I also mentioned, we are leveraging investments right now in the precision landing, the modeling, the plume surface interaction, and that Lofted flight test. So those are ongoing activities which are really going to help us with these next big leaps. I'd say the next thing we need to get started is really understanding that large-scale flight test at Earth. We need to understand how big it actually needs to be to give us relevant objectives and environments for the Mars vehicle. So that formulation of that flight test is one of the major next steps in my mind.
Great, thanks. That's exciting. All right, let's hear from Adam and talking about Mars 2020 and our long history of robotic missions to Mars.
Thank you, Tim. Next slide. So by way of a bit of a background, I am currently the chief engineer for the Mars 2020 mission, the Perseverance rover. I have worked on a great deal of robotic missions to the surface of Mars, from Pathfinder, Mars exploration rovers. I've been involved in parachute design and entry descent design, and I led the team that developed the Sky Crane landing system and entered Curiosity and safely landed her in 2012. There is a long history. This slide here shows the most official Mars program history, but there are landers that preceded the existence of a Mars program, that being Viking in 77 and the Phoenix lander, which was kind of a bit of a Viking clone, in 2008. All of the surface missions have shared many similar components when we're operating at this size scale of robotic spacecraft. Next slide. It's all really, in the end, about energy management. If you're coming from Earth to Mars and you're going directly, you show up going about 10,000 miles an hour or so. For Perseverance, it'll be 13,000 miles an hour. It was that, a little bit over that for Curiosity. And you dissipate all of the energy in the first interaction with the Martian atmosphere, that is to say, the entry process, where you develop very high heats of friction with the atmosphere. We put our spacecraft in capsules and reject that heat largely to the atmosphere. And that process slows us down from about 10,000 miles an hour to orders of magnitude about 1,000 miles an hour. That's, of course, not slow enough to land on the surface of Mars. So at robotic scales, we open up a second stage aerodynamic decelerator. In this case, it's a parachute system. If you can click the next slide, you can see that 99% of the kinetic energy that you show up with gets dissipated by the aeroshell, and about 99% of the remaining kinetic energy gets dissipated by the parachute system. That leaves you on orders of magnitude about 100 miles an hour, really closer to 200 miles an hour, 180. And that's still, of course, not slow enough to land on the surface of Mars. So every expedition, Viking, Phoenix, Pathfinder, MER, you name it, has then gone on to a propulsive element. And that propulsive element takes out almost all of the remaining kinetic energy. And you're left, depending on the technique you've used to slow down, how fancy your rocket system is, whether you've got throttles in your engines or whether they're solids, how good your telemetry is with your ground relative understanding. Are you just using velocity? Are you using range? Are you using range rate? And depending on which set of equipment you have, you're left with a residual error, a little bit of velocity left over. And for that, you need a touchdown system. We started with legs for the Viking missions. They were very similar to the legged landers that we'd used to put astronauts on the surface with Apollo. We evolved or changed or went to additional techniques. We used airbags for Pathfinder and for Mars exploration rovers, the rovers Spirit and Opportunity. And that was because we didn't have a sophisticated propulsion system and avionics system. And so we needed to go with a more robust touchdown system. And then by the time we got to Curiosity, the largest rover to be put on another planet, she was so big that airbags wouldn't work. And a landed system with legs was too massive. And so we developed a novel approach of using the sky crane, which I'll touch on in a second. It ends up being that many times the engineering of that final piece of the puzzle that takes out almost none of the kinetic energy, but does interact very, excuse me here, there we go, does interact very intimately with the Martian environment, that final touchdown system takes a tremendous amount of engineering effort. Next slide, please. In Curiosity's case, and what will be again in Perseverance's case, that final touchdown system involves the sky crane, where we hang the rover, because it's built to interact with this unknown environment of the Martian surface, below the propulsion system and gently set it down on the surface of Mars, approximately 1.5 miles an hour, 0.75 meters a second, plus or minus. And that having started from 13,000 miles an hour. Next slide. Although Perseverance and Curiosity look very, very similar to the casual observer, and they are quite similar in their size. Perseverance is a little bit larger and a little bit heavier. We have added a cool feature. Michelle even mentioned the importance of it for future entry, descent, and landing efforts. A cool feature that we call terrain relative navigation. Next slide. Where we are going, where scientists would like to go on Mars, is typically treacherous places to land. And in the Curiosity mission, we ask the question, when you look at a piece of Mars that is dangerous, has got lots of terrain-related hazards, are those hazards generically present everywhere, or are they punctuation marks in a surface that is largely not dangerous? And the answer came back when we studied it, that we discovered that generically Mars is safe to land on, but it can be punctuated by specific sites, specific places, cliffs, large rock fields that you would like to avoid. A great example of this is the place that we've chosen to land for Perseverance rover in 2020. That is to say, on February 18th of 2021, we'll be landing in this ellipse you see here, essentially on top of the delta in Jezero crater. That delta provides the scientists with exceptional material to sample and produce samples for eventual return to Earth by the next legs of what will be a Mars sample return effort. In some sense, we are doing the first dry runs of what would be necessary to take humans and put them on Mars and return them safely from the surface by doing that with samples that we take from the surface of Mars. The technology that we need to be able to land in places like this is called terrain relative navigation. Next slide, please. What TRN does is takes images while we are on the parachute and compares those images to images it has in storage that have been taken from the HiRISE imager in orbit around Mars as we speak. When it compares its own images it just took against the map it has on board, it locates itself. Then it looks at a set of risks that the engineers have loaded into the spacecraft, a color map, as it were, that tells the spacecraft where the dangerous punctuation points are on the surface of Mars and where the generically safer places are. And when we go and take our propulsive divert, which we need to do so that the parachute doesn't hit us on the back of the head, we divert to the safest possible location, massively improving the statistics of the surface interaction and allowing us to land in exciting scientific destinations like the Jezero crater. Next slide, please. So, February 18th, 2021, few short months away, 12:36 p.m. Pacific time, no light delay. That's to say, that's when the actual event is going to happen. The rest of us on Earth here will find out about it about 10 minutes later as the information from the rover streams down to us. Feel free to follow along at mars.nasa.gov or either of these sites for last minute and up to the minute details. Thank you, and we'll take any questions.
All right, thanks, Adam. So Perseverance, really interesting mission, getting ready for Mars sample return. What's your most favorite part or most exciting part of that mission for you? Is it the sky crane part because you were a co-developer?
Well, certainly
or something else?
in terms of excitement, that is to say the amount of adrenaline that is secreted into your bloodstream, nothing tops entry, descent, and landing, which is unfortunate. It's the risk not hold and must drag the entire mission through to enable our survival. But in terms of new steps, I am very excited about terrain relative navigation. It's a major step forward, and the beauty of it is it uses kind of generically available cameras and some fancy software, but it doesn't require hardware technology of any particular great level. And of course, I'm also quite excited about the prospect of taking samples. Yes, we have a very complicated and sophisticated sampling system, and we're going to take samples for eventual return to Earth. That pathway, the sample hardware's trip from Earth to Mars, having a sample put in and returning to Earth, is the real progenitor of human boots making the same trip.
All right, thanks, Adam. Okay, let's go now to Ashley.
Great. All right. My name is Ashley Korzun. I'm just delighted to be part of this this panel here today and talk to you about, I know Adam just said, EDL, there's nothing like it. And I have to agree. I was fortunate to work on the InSight Mars lander, and I can't imagine that feeling ever gets old of watching something that you've put your heart and soul and blood, sweat, and tears into touch down on the surface of Mars and see those first pictures come in. So from looking what we're doing with robotic scale systems up through what it's going to take to put blueprints on Mars is something I've been really fortunate to have basically been exposed to since the first day I started graduate school quite a while ago. At this point, and was able to do internships. Saw a lot of students on the line in the earlier sessions. That's how I got my start. I interned at Goddard Space Flight Center. I'm working on totally non-EDL related things, but you got to touch some space hardware, which was great. And then, while I was studying EDL and specifically retropropulsion all throughout my graduate work, I was able to spend a lot of time at NASA Ames. I spent time at JPL and spent time at NASA Langley before finally taking a job there at the end. So I've been working full time for about 8 years. And a big part of that work has been, what do you do about all the technologies that Michelle highlighted in her talk? How do we bring those to something that we can work with Adam and his folks at JPL and other spaceflight centers to turn into reality and actually get us further down that path to Mars. Can we bring up my charts, please? Awesome. So I have to use the retropropulsion image on the first chart because I am a bit of a retropropulsion junkie here. But I'm going to talk, really building on what you saw in Michelle's presentation here, just over the next few minutes. We're going to look at each phase of entry, descent, and landing, and some of kind of the unique challenges associated. Why did we need to be looking for new solutions for ED and L, and kind of where are we in the technology development spectrum for that? Next chart, please. So we'll start with entry. Michelle talked about inflatable aeroshells, or the hypersonic inflatable aerodynamic decelerator, or HIAD. You have this deployable aeroshell. It has an inflatable structure, but behaves as a rigid shape during that atmospheric entry phase. So that first 99% of the kinetic energy you're getting rid of that Adam talked about. But you also have then a flexible thermal protection system or heat shield on the front of this vehicle to protect you against those heating. Mars has an atmosphere. It's thin, but it is still enough to cause you some challenges from a heating perspective and require you to do something special to protect your payload. Why are we looking at inflatable decelerators? Michelle mentioned it as well. You're constrained. You have a finite diameter for a launch vehicle. It's quite sizable, but when you start talking about the size of the payloads that we want to put down on the surface of Mars, you want to go as big as you possibly can. So with an inflatable system, this allows you to have a much larger aeroshell and heat shield or drag device than you would otherwise be able to fit with a rigid system inside that same launch vehicle. What does this buy you? I saw someone posted a question that was flying through about ballistic coefficient. Think of this as a way. The larger this drag area of your vehicle, you're still considering mass there, but it allows you to trade the amount of mass you can deliver to the surface, as well as surface access. Maybe you need to land at higher altitudes, depending on what sites you're trying to reach. So this gives you the ability to make those types of trades and still end up with a closed design. It also, by going to that larger diameter, larger drag area, reduces your peak heat flux, by allowing you to do more of your deceleration in the less dense upper atmosphere at Mars. And we've already touched on the launch vehicle fairing there. I like to use these pictures, though, in that lower left to give you a sense of scale. Lofted, I'll talk about here on the next slide, but this is a 6-meter diameter HIAD. For reference, what we're talking about for aero capture or entry at Mars, these are 16 to 18 meters in diameter. So we're getting there. But even just seeing, next to a person what 6 meters looks like, these are very, very large systems. Next chart. So specifically, as this is our next upcoming technology demonstration mission, is Lofted, the low Earth orbit flight test of an inflatable decelerator that Michelle mentioned. Our orbital entry conditions, it's about 8 kilometers per second. Kind of depends on how we do its separation from our ride. We're riding on a ULA vehicle, and we're a secondary payload to the JPSS-2 weather satellite coming up, but this is that 6-meter diameter HIAD that you saw on the previous chart. So this is going to be with Mars relevant heating on the largest system of this type that will have ever flown at 6 meters. So still smaller than what we're talking about for the Mars human scenario, but a huge step forward in terms of how do you manufacture these systems? How do you test them? How do you qualify them? And then how do you prove their performance in a terrestrial environment? Next chart. So next we're going to transition to descent. As we've mentioned, you're not going to use parachutes for human scale systems. It's going to be an extended propulsive phase of flight, where the primary purpose is to decelerate the vehicle, but you're also using it for, on that precision landing path as well. It's a very, very complex system, of what's going on when you have these very large rocket engines exhausting upstream of the vehicle. This enables you to land more payload mass than you're able to do with supersonic parachutes. It's particularly advantageous for Mars specifically. I've mentioned you've got a little bit more control authority during descent and landing. It's kind of your big hammer in terms of cleaning up errors due to uncertainty in the atmosphere when you get to Mars, so on and so forth. But you do have the potential for significant aerodynamic effects on the vehicle during powered flight, and these can impact critical sensor performance as well. We get asked a lot, folks have seen what SpaceX and Blue Origin are doing, and there's a lot of work in Europe going on as well with reusable launch vehicle boosters. Those are very slender vehicles where essentially all of that drag area on the base is taken up by the engines. Launch vehicles are really, really good platforms for a number of reasons for retropropulsion, and that's why you're seeing so much success. And it's completely game-changing, the reusability that's being derived from this. But I will draw your attention to something that is different in this case, and that's that figure in the lower right. That orange ring, that is your heat shield. You can see itty-bitty little engines in there. So this is a very, very unsteady, very dynamic problem. The difference in our case is you have a lot more drag area, much larger moment arms with which you have to combat vehicle stability and controllability during this phase of flight. So that's just one difference I wanted to highlight it. Next chart. Okay, we are at landing. You're still on retropropulsion, and Michelle mentioned this as well. Plume surface interaction, and I'm sure Adam can speak to some of the, some of those images that came back from Mars Science Laboratory too, where right on the deck of the rover you have debris. We didn't send it there with the debris. That debris came off the surface of Mars, was lifted up by those sky crane descent engines, and its final resting place was on the surface of that vehicle. I'm showing images in that lower right actually from the InSight Mars lander. Larger pictures from the surface there. The landing pads are almost completely covered in Mars regolith. The average crater diameter, and InSight's as a small robotic lander. Those craters are 20 inches wide by 7 inches deep. In fact, one of those landing pads is almost in a crater from the descent engines. InSight had a very strict tilt requirement in order to achieve its science. And if it had fallen into that crater or slid down in there, the science mission could have been in jeopardy. The Apollo lunar landers, this was a huge problem as well, not just for the crater that's formed underneath the vehicle, but the obscuration of your views, whether that's a crew in the loop during landing, but you have all these sensors on board as well for precision landing and hazard avoidance. Is there, are you potentially causing damage to those, or are they behaving as you need them to perform to ensure success of your mission? In addition to all of this, even before you get to touchdown, the effects from that rocket exhaust plume hitting the ground and turning back up and coming back toward your lander can cause vehicle instabilities that you're going to have to contend with as you're trying to reach a safe and soft touchdown on the surface of Mars. Next chart. So if we look at the moon to Mars, there's a lot of activity in lunar exploration going on right now with lunar landers of all scales, lots of commercial activity there as well. They're going to the moon, as soon as this time next year, we're going to be seeing, moonshots, and they're going to become pretty regular. All of these systems use some form of powered descent, which is great. This is absolutely a point of departure for a lot of challenges that we face in, what's going to be necessary for an EDL system to put humans on the surface of Mars. Things like long-term cryogenic storage, engine performance for engines that have been kind of in storage or exposed to space environment for those types of things. How do you do guidance and navigation control with these extended propulsive phases of flight, but doing precision landing and hazard avoidance, different types of sensor suites, different types of information you've got to deal with. All of that, the moon is going to be a great launch pad for. But all phases of EDL at Mars are critically impacted by the presence of the atmosphere. Really hard to do testing here at Earth, really hard to do, testing at the moon as well that will feed forward in a complete system sense at Mars. But there's still a lot that we're going to learn, particularly over the next 3 to 4 years with lunar exploration and how all that feeds forward. So with that, I will go to just my last chart here. We've talked about all of this. We've got all new technologies, that a lot of them draw heritage from their predecessors, but some are completely new for enabling human scale EDL at Mars. EDL itself, it's really challenged when you start to look at the constraints you have from that larger exploration architecture. So, the panel this morning talking about, there was one, I think, yesterday on ISRU, and then, ECLIS and things like that. All of those start to factor in, and they do eventually affect what you're going to be able to use in terms of common technologies on your EDL system. But all of this, Michelle showed that roadmap. It's something that we're going to need everyone's participation, if we're going to be successful and continue getting closer. We're really inside that 30 years to Mars ceiling. We're closer than that now. So it's truly an exciting time to work in this field. And with that, we will see you on Mars. I think that was my last chart.
All right. Thanks, Ashley. So what's the most unique or unexpected thing that you've learned during your supersonic retropropulsion research? What really surprised you? A new finding or something?
So it's not a new concept. NASA did a lot of research into it in the 1960s up until the 1970s. So if you're familiar with the literature, there's this big gap, that there's just nothing. Why is that? Well, parachutes are always going to be more mass efficient. So when they realized that supersonic parachutes were going to be the answer to enable the Viking landers, all of the work, it largely stopped. And then as these human Mars architecture concepts, increase in fidelity interest in this topic has resurfaced. What we knew 10 years ago is completely different from how we thought we might utilize this system today. So to watch that evolution, from what you do in a wind tunnel to what you're able to simulate, and then all of a sudden someone comes back with these constraints that you didn't get to choose, and it completely changes, what our path looks like to a flight implementation. So, just understanding this isn't a we just go and do it. It is an engineering problem, but the continuous evolution of our understanding of it, and just understanding what a powerful tool or big hammer in your toolbox it will be to enable humans to Mars has been great to participate in.
All right, thanks. So now I'm ask some questions. I've got some of my own from your presentations. We've got questions coming in from the audience. I'll probably jump around, and feel free to jump in. Now let's make this a discussion. So I think, Adam, I'm going to start with you. I don't know. Have you had a chance to look at any of the flight data from Perseverance on its way, or the launch campaign, and anything that surprised you or is interesting? Because I know, when you finally get a bird up there flying, it's always something comes up.
Right. Yeah. We have absolutely looked at the data, and we look at it. We're looking at it. It's being looked at as we speak right now, in that window right there on my screen. We had what we call an ISA. We had an anomaly just after exiting eclipse, early in the spacecraft, just after launch, and we saved. We've had a couple little cranky bits and pieces. They have not ended up being substantive. They are always terrifying, and we work 24/7 to get the spacecraft state understood and recover when any saving event happens. But so we've had some first couple of weeks actually was pretty exciting in a way we don't like. But we've sort of entered a more quiet period, and cruise is progressing beautifully. Trajectory is great. The launch vehicle did a fantastic job, really put us right on the money. So we're looking good right now. Everything's looking pretty good.
All right. Yeah, that sounds like at least every normal experience I've had with a new spacecraft. So I'm glad she's settled out and on her way. All right. So let's see. So a lot of interesting data here. And one question that I had, and I saw some audience questions about it, and maybe Michelle, this is for you, maybe for Ashley, but the 20 metric ton payload size, what drives a Mars landing payload size? And I know it's varied in the different Mars studies over the time. So I thought, Michelle, you could comment about, well, what size is that 20 metric tons?
Sure. Lots of things size that 20 metric tons, as you might imagine, but really it's one of the biggest drivers is crew size. So I believe back in DRA 5.0, we were looking at a crew of 6, and we've reduced that. I think that's still under some amount of trade. And we've also been looking lately at opposition class missions as opposed to conjunction class. So that means that we would only be spending up to 30 days in the vicinity of Mars instead of a year and a half. And we may even tailor the amount of time spent on the surface below that 30 days to, try to minimize the surface logistics, the number of failures that we might see. So, trying to find that sweet spot of a productive mission of exploration with trying to manage the risk and the amount of mass that we need to send. So once you do that, it's a matter of breaking up the various payloads into reasonable chunks that can be launched either on SLS or a commercial rocket. And, the ascent stage is the largest indivisible piece that we need to land. So it's all about the mass and volume of that ascent stage to get the astronauts safely off the surface and back towards Earth. So those are some of the big drivers that we see on the payload size.
I assume it gets easier if you go smaller. Is there a break point as you go larger that we'd have to be using different technologies?
So the interesting thing about the HIAD is that it's very flexible. When we were looking at the rigid, more slender vehicles that fit just inside the launch shroud, and we call them mid-L over D vehicles, so they're more long and slender. They will have packaging constraints and volume constraints. So there'll come a time when you just can't package your payload into a given diameter and put the center of gravity in the right place to ensure a stable landing without having, legs that are wildly spread out. So we have not found a break point with the HIAD technologies yet, but on the other hand, we have not scaled up beyond the first 3 tori of the 12-meter scale that Ashley showed you. Actually, she showed you Lofted at the 6-meter scale, but we have manufactured the first 3 inner rings of the 12-meter scale. So until we do that, I don't think we quite understand what the real breakpoints would be. But from a paper engineering standpoint and simulation standpoint, the HIAD is very flexible and doesn't seem to have any inherent breakpoints.
Great, thank you. And maybe this question is for Ashley. Michelle, you had mentioned about, Lofted was getting Mars relative heating at Earth. How do you do that?
You want to take that one, Ashley?
Do you want it, Michelle, or do you want to? Okay. So we hitch a ride on a launch vehicle from Earth, so you can tailor your entry profile, at Earth, and all of that is, of course, adjusted for the composition of the Earth's atmosphere being different, as well as the density of the Earth's atmosphere being different. So things like radiative heating that we would worry about at Mars, that you don't worry about so much as at Earth, that is a harder match. But you're able to tailor that entry profile and get, heat rate and heat load. You can get a pretty good match, here at Earth, for that entry phase. Where you start to come in is if you try to do more than just that entry phase. Landing at Mars is like landing at 100,000 feet at Earth. So it is very difficult to tailor yourself a ride here at Earth that would actually give you that kind of a prolonged test phase, but you can traverse relevant conditions. And that's what we're doing with Lofted to match heat rate and heat load.
Okay. And after you pass through the sort of the testing window and get your data, what's going to happen to the vehicle?
Sure. So one of the other great things about Lofted, and this feeds forward to Mars sample return and the Earth entry vehicle as well, is that our end of experiment for Lofted is about Mach 0.7. At that point, we have an ejectable data recorder that will get booped off the vehicle and will be recovered out of the ocean. But we will be continuing to take data all the way down until there's a parachute that deploys on Lofted. Very, very low subsonic conditions. So for fully passive systems like the Earth entry vehicle and the Mars sample return architecture, understanding how these types of shapes fly, more or less passively all the way through transonic to subsonic conditions is going to be a really valuable data set there. And we do plan to recover the vehicle upon splashdown as well. So we should have redundant data sets, but all the way down.
Great, thanks. That's great that you're combining tests and saving the vehicle, but being prudent just in case. So, and one of the things that I'm hearing is that there's a lot of different reasons that designs evolve. There's breakpoints for mast, parachutes don't work. You got to go to supersonic retropropulsion, this and that. And I was wondering, for this one's for you, Adam. I think going to the sky crane was one of those. Oh, we need to get bigger. What are we going to do? Can you tell us about the genesis of the sky crane idea and how did you come up with that? Tell us that story, because I think it's very not the specifics but relevant for how engineers make these design decisions and come up with the next new thing. Adam, look.
Wow, great. Yeah, sure, Tim. Can you hear me?
Yep, I can.
We were in a bit of a pickle. We had the first three pieces of the puzzle done, right? The aeroshell, we had the parachute system, we had the propulsion system, but we didn't know how we were going to do the final piece of the puzzle at the Curiosity, at the 1 metric ton length scale for a rover in particular. And we struggled. We looked at airbag systems, we looked at legged lander systems. And the challenge that we had, as Michelle mentioned, we even had a challenge at the 1 metric ton packing into aeroshells, 4.7, the 5 meter class aeroshells, which is what what humans currently make, and we were at an impasse, and we got everybody together that had participated in the previous several years, putting Martian hardware on the surface, and looked for that third way, that new way. And it actually started out, the easiest way to describe it is we started out with the idea of an airbag lander that had a propulsion system and a set of airbags with the rover inside underneath it. And we tried to add the functionality to the propulsion system to eventually reduce the need for the airbags, because airbags don't scale well mass-wise. It's one of the challenges of inflatables. Inflatables are bubbles. They have a certain surface scaling disadvantage, and we looked at that once we had added the technologies, that is to say, throttleable engines, a radar system that could do Doppler to the surface and had very good range accuracy, we had bought all the complexity we needed to eliminate the airbags, not just reduce the level down so that we could get airbags not to break, but actually eliminate them, which is always a good thing. If you can eliminate a thing, an element of your spacecraft development, you've eliminated a ton of risk, cost risk, mission risk, the whole thing. And we stumbled upon it. There was about a dozen of us in the room. We stumbled upon it one day in a brainstorming session, and we kind of immediately knew that, one, sound engineering principles had driven us to this position, but that, two, every time we spoke about it, people would say it was crazy. And that's what people said. In fact, Mike Griffith, the NASA administrator at the time, said it was crazy, and he hauled us into headquarters to tell him why we thought it was the right thing to do. And eventually he said that maybe it was the right kind of crazy. So it was a sort of circuitous way. We were kind of surprised by the result that we ended up with. But history has borne out that it did the job, can do the job.
Thanks. So you didn't want to just make it look like it's wrapped in bubble wrap? That wasn't the right solution.
Well, you have
tiny little airbag.
Always have to get out of the bubble wrap, and getting out of the bubble wrap can be a bit of a big deal, like the biggest of deals. I think there'd be few greater acts of embarrassment than waking up with your rover on the surface of Mars and having it inextricably tangled in the airbags that it got to the surface with. So, and also, again, they work poorly. The airbag system works poorly in a scaling sense, and the mass goes up quite quickly.
Oh, okay. Great, thanks. And so I think that brings up a question, and I've seen a couple in the audience Q&A about the HIAD system and not getting rid of it before you land and needing to retract. And I think maybe, Ashley, this is a question for you. What was the thought process there about making the decision to hold on to HIAD instead of ejecting it?
Sure. And I'm sure if I forget some things here, Michelle can help as well. You may have seen some of the prior architecture studies that had been released that we did have jettison events, or kind of where the vehicle does a significant transition. Doing transitions like that is extremely risky. You do not have a lot of time at Mars. Just as an example, Michelle mentioned you're on your engines, you're flying near horizontal, but you're not very far off the surface. If you miss engine initiation by even 1 second, you're now a kilometer or more downstream of your intended landing target. So having to do those types of transitions not only introduced risk due to just the complexity of the maneuvers themselves, the timeline is a huge concern. One of the benefits of maintaining the HIAD in particular on the vehicle, we've mentioned as you get closer to that surface, you're going to start kicking up all sorts of debris, dust, particles of all sizes. Some of them are going to be traveling extremely fast, and it could otherwise damage your land or critical architecture elements. So if the ascent vehicle is your payload, in that case, the last thing you want is to put a hole in one of those fuel tanks with a rock you kicked up off the surface of Mars, because there are not going to be prepared landing sites when you get there. And these are very large landing systems. So having the HIAD on board, you can see it a little bit in that inflatable structure image, but there are all sorts of straps behind there that give it that rigid structure when it's inflated. So as you deflate that system, you have a natural system already in place with which you can withdraw the HIAD under the vehicle. So you've got additional protection, from those engines while you are flying, but also from the debris you're kicking up on the surface. But just the less transitions you have to do with your vehicle configuration at Mars, the less risky it's going to be.
And how does what's the kind of the interface between the rockets and the HIAD? Like, they got little windows for them, or how does that work?
Sure. So, and Michelle touched at it too. You have this rigid nose cap, and that rigid nose cap is what fills the launch vehicle fairing. So a big chunk of that diameter is a rigid piece. It may have a flexible, conformable TPS on the front of it, but it's still a solid piece back behind there. So your engines are going to be mounted and directly intersect that rigid piece. But you're going to have some sort of door, some sort of blowout plug, some sort of device that opens, once you get through that entry phase that does expose the engines.
Great, thanks. And Michelle, I saw a question about ballistic coefficient. And actually, what is the ballistic coefficient of the HIAD, but also what is ballistic coefficient and how does it compare to other things?
That's a great question. Yeah, and I tried to answer it in the chat. So ballistic coefficient is kind of the ratio between, the ratio between the mass and the surface area of the vehicle. So it's the difference between, a glider and a blunt vehicle. So we had looked at different systems, as I mentioned, for ballistic coefficient. I think it might have been on my first chart, but the ballistic coefficients of all the landers that we've sent to Mars successfully thus far have had ballistic coefficients, in the 100 to 160 kilograms per square meter range. And so one of the things that is attractive about the HIAD system is that we can make that surface area large for a pretty low mass and keep that ballistic coefficient even for a 20 metric ton payload in the vicinity of things that we've flown at Mars before. So that gives us, a little bit of extra experience with how this will fly and how it might behave relative to what we've done in the past. So that's very important for, building up this type of capability incrementally. And back on the question to Ashley about why hang on to the HIAD, but besides the timing, we started thinking about, as we aggregate assets in a region to enable an exploration mission, that HIAD and everything attached to it is probably several metric tons. And so if you're ejecting that, now you have to make sure that it's done far before you get in the vicinity of other assets because you don't want it hitting anything. So then it becomes a fully guided autonomous vehicle within itself, which is also very difficult to test and certify at Earth. Ashley talked about the difficulty in matching the flight profile for Mars at Earth because of the difference in the atmospheric density. So, some of the risks of being able to certify that and building a whole nother almost autonomous vehicle are a couple additional reasons why we decided to hold on to the HIAD.
Great, thanks. And what's the HIAD made out of? I'm sure there's all kinds of different materials and the different structures, but in general, what's it made out of?
You want to take that one, Ashley?
Ooh, yeah, I work more on how it flies than how it's constructed, but I do know a little bit about that. I'm not sure what the exact materials are, but if you kind of go from the inside out, it starts with a gas barrier. Essentially, you have some sort of bladder, some sort of high temperature bladder, and that's what your inflation gas goes in. And when pressurized, that's what gives you this rigid structure. On the outside of that, you have an additional, high temperature and durable. They are still textile, so these are woven pieces in which side this gas barrier is inserted, and those come together. And then you have these additional straps that give you, very, very strong, very, very rigid structure. If you ever have a chance to go up to one of these, we have a traveling HIAD that we take around to various events. You really get a sense that these are not balloon animals. These are not, wacky inflatable tube man that you see being inflated outside of a store. These are very, very rigid structures. And then on the outside, you have multiple layers of a flexible TPS. So this is something that can be folded, it can be crushed, it can be, but essentially packed very, very tightly, prior to deployment and stored that way for quite an amount of time. They're predominantly insulating layers, on the inside, because by going to a much larger vehicle, you are able to reduce your heat rates considerably. So it is this kind of this buildup of flexible but rigid when under pressure and high temperature materials.
Neat. All right, let's talk about landing accuracy for a little bit. So Adam, we saw in your charts that terrain relative navigation is really making an improvement. How much of an improvement between Curiosity and Perseverance are you expecting? I know this is the first time you're using it.
Right. Well, there's a couple of pieces to that. The accuracy or the size of our landing ellipse isn't affected the way we're flying by terrain relative navigation, because we do not do the terrain relative navigation piece until we're on the parachute. And once you're on the parachute, you've already committed to your locale, the county that you're in on the Martian surface. It ends up being that we're doing another trick I didn't mention to reduce some of that ellipse size. We use guided entry for both Curiosity and for Perseverance. We have lift. We fly the aeroshell, a symmetric shape, at a canted angle. That cant produces lift. We store that lift and move it back and forth, up and down, to affect our trajectory through the Martian atmosphere. So that allows us to shrink the ellipse meaningfully from of order 100 kilometers to of order 10 kilometers. For 2020, for Perseverance, we will also add position to the algorithm that we use to open up our parachute. So if we've reached the right parachute conditions, but we are still high and still up track of our position, we will wait to open the parachute until we're right over the center of the ellipse. So that additionally helps us shrink the landing ellipse. What we use terrain relative navigation for is to avoid hazards. But that said, our divert allows us to hit about a 40-meter patch on the surface of Mars. And so when one imagines doing some of the follow-on missions that we're currently working, the missions that will bring the samples home, we intend to place enough fuel in the follow-on landers to make the divert, which for us is of order 500 to 700 meters, to allow that divert to be as large as a few kilometers. And then that allows you to get from any place in the ellipse to a central location, or do what we call pinpoint landing. So the terrain relative navigation allows us to get down to about 40 meters of accuracy. That includes all of the various elements, camera uncertainty, map uncertainty, position uncertainty, execution of the divert uncertainty. And we think that it will stay at around that level, 40-ish, maybe a little lower. And just with the addition of fuel,
Hey,
the
Adam.
follow-on missions will be able to get to pinpoint. Yes.
Okay. Hey, Adam.
Yes.
You're a little choppy.
Okay.
So I think what I heard was that you're using terrain relative navigation to be able to look for hazards and divert. But maybe it would be good for you to. Well, I'll let the tech folks work with you on your IT because you're just being a little choppy in the video. But why don't you try now? How is it now? Oh, yep, still choppy. Okay, I'll let the IT folks work with you in the background. And let me ask the question now for Mars. What's the requirement for landing accuracy for a crewed mission?
We're currently carrying 100 meters diameter, so 50 meters from the point. As Adam described, we might be able to do much better than that. We're working on a number of precision landing technologies right now, and again, this will be something that can be tested on the moon, although obviously the trajectories and the presence of the atmosphere in the system will be much different at Mars. But we are looking at terrain relative navigation, precision velocimetry, and hazard detection LIDARs for places that don't have as high resolution maps as we might need. It also gets a little easier when you already have assets in a location, because you can navigate relative to those or have beacons on them. So actually landing, next to something that already exists is a huge advantage. But we're looking at those very precise landing conditions, as you can imagine, for landing things near each other to build up our surface infrastructure. You'd hate to get there and be just out of reach of the cord from the power system. So, and we also need to be very careful, as we've talked about, plume surface interaction. Some of our predictions say that our ejecta could go up to 700 meters away from our landing site. So we need to be in the middle of our area so that we don't sandblast our neighbors as we land and damage other equipment.
Oh, are you thinking about some way to protect the other things you're landing nearby? Like
there are lots of ideas, and we're starting to do some concerted work within space technology on that, particularly for the moon, putting humans there first. So there are a number of different ways to potentially make landing pads or berms, but there's always going to be a first lander. So that one won't be so worried about blasting its neighbors, perhaps, but we still have to protect the lander that we're in. So understanding that environment, that induced environment, both heating, pressure, and the ejecta is one of our major objectives as we progress towards putting humans on the moon. And that knowledge and instrumentation will feed forward to Mars to some extent.
Yeah, that's great, because landing on the moon, we're going to have the same issues with debris as we touch down. Does the type of soil on the moon and Mars, that difference, or the atmospheric difference, how much of a does that make a change in your analysis? Is it minor, or is it a really big deal?
It's a pretty big deal. The moon is a vacuum environment, so the physics you have to model are fundamentally different to get basically your boundary conditions correct for that problem. So it is a different set of physics just by nature of being in vacuum. Mars is very low density, but it's still an atmosphere. But then just on the regolith side of it, the moon is very, very cohesive, very irregular. The particles in the soil really like to stick together. They're very jagged. It's why lunar dust is such a huge problem. It gets everywhere, and it gets into joints, and it just destroys things. The same goes with what physics and what does it take to make a crater on the moon and get those particles to separate and be lifted away. Is quite a bit different than what we know about the regolith on Mars, which seems to be something closer to a silica sand, still irregular but a little bit smoother, not quite as jagged. So all of that factors into our analysis, but all of the test data we're gathering and the testing we're planning is considering for both destinations. So we will have the capacity to predict, cratering and ejecta for both the Moon and Mars environments.
All right. Let's see. So, and let's talk a little bit more about sort of those differences. And now you talked a little bit about the differences between, propulsive landings on Mars and on the Earth. Talked about how you got a very large drag area for the HIAD that makes it more unstable. Is the atmospheric differences between Mars and Earth a big deal as well in the retropropulsion?
It does start to factor in. There's a lot of, you could do some scaling and make them fairly similar. One of the challenges we face in the Mars scenario, we've mentioned these other elements, especially that ascent vehicle in the architecture. This is a really big activity. You're going to want to do kind of as much common technology development as you can. Propulsion systems are one area that it would be great if you can do a common technology development. The physics, and what those plumes look like for, optimized for what would be a very high altitude Earth ascent case, which would be ascent off the surface of Mars, is pretty different than what it would be for a lot of our propulsion systems here at Earth. So the plume physics themselves, the plume structure of your engine exhaust, all of that affects basically how dynamic and how extreme the environment that your vehicle is flying through. So there are ways to do that scaling. You've got to go to very, very high altitude at Earth. It's tough to terminate a flight test, at 100,000 feet, essentially bringing yourself to almost a complete stop. So, there's a lot of things. You're never going to get perfect scaling. You're never going to demo the end-to-end system here at Earth. But can we do large Earth-based flight tests to do critical checks and match really important physics? We can.
All right, thanks. And another question from the audience, talking about recent research about reducing sonic booms. And I think, let me find the question here. The research was from Christine Darden's research. Are you familiar with that research, and is it helpful for this purpose?
I'm loosely familiar with the research because NASA Langley does a lot of work with supersonic transport and specifically sonic boom reduction. So it's absolutely critical research for terrestrial flight. It's not something for our retropropulsion application that we've seen a lot of extensibility to, but fundamental physics is fundamental physics, and there's always critical information and knowledge to be gained from research in those types of areas. The difference lies is there was a lot of historical work on using what we would think of now as retropropulsion to reduce the severity of a heating environment for a slender entry system. But when your primary purpose is pointing the vehicle in the right direction, guiding it to where you want to go, and really slowing the vehicle down, those types of effects and those that are much more common with, say, a sonic boom reduction type of experiment and those associated physics is just a little bit different.
All right, thanks. Adam, did you make it back in? Oh, doesn't
I
look like you made it back
did.
in.
Can you
there
hear
you are.
me?
Yes, I can.
Great.
All right, that's great. Question for you, and actually, I'm not quite sure we finished the landing accuracy. You were talking about terrain relative navigation and how it allows you.
Let me take a swing at landing accuracy again, slowly and succinctly. Terrain relative navigation and a propulsive divert can allow us to reach approximately 40 meters of accuracy in the placement of the spacecraft. We anticipate that in the Mars sample return campaign, we may add additional fuel to the follow-on spacecraft that is going to pick up the samples and use that fuel to lengthen the divert and make the divert approximately the size of the radius of the landing ellipse. And in doing so, reach what we refer to as pinpoint landing, which means coming in from entry, we can hit a place to about 40 meters of accuracy.
Nice. All right. And another question came in about, and this is much more of a landing site selection question. Why we know that there's water all over at Mars. We've got some indications of where there might be past life. Why don't you target to land as close to the place you want to go, land near the water?
The simple answer is international law. Via UN treaty, the US has agreed to the planet Mars, Earth, and specifically to protect special regions of Mars. And any place where there is liquid water or the possibility of liquid water is categorized as a special region. Think of it as like a national park. And just like a national park, you can't just do anything you'd like. And in our case, for special regions on the surface of Mars, we are not allowed to go there unless we meet a set of cleanliness requirements that, frankly, in the modern epoch, we don't know how to meet.
All right, thanks. Okay. So another question from the audience was about our modeling and simulation capabilities, but for visualization purposes. Like, do we have enough remote sensing data or enough analysis that we could use something like artificial intelligence to create a visualization of what it would look like to be landing on Mars? How accurate are those simulations? Anyone?
Well, I'll take a crack at it. We report in our robotic missions, we report one way of communicating the progress of one of our robots to the surface of Mars is by showing the real-time data and then visualizing it. It is quite possible to create three-dimensional maps, digital elevation maps of the Martian surface. We actually intentionally stop short of creating photorealistic simulations driven by our actual flight telemetry for fear that the public of the United States might mistake that for the actual thing. So the data is largely there to allow us to do some pretty phenomenal simulations. And you can find at the websites I described flyovers of the Martian surface that are, pretty much like you'd see if you were flying over, resolved to about a meter in spatial resolution. But we don't use those in our displays of landing for fear that people may confuse fact from fiction. That seems to be going around.
So
right,
if I could just add to that just a little bit, it's an interesting idea to try to merge art and engineering for visualizing something like that. We do have, as Adam said, a lot of information about our environment, and that's where our community comes in terms of, understanding the chemistry of the atmosphere that we're flying through and the heat that is generated as we fly through the atmosphere. And we could, and actually we did it in concert with a museum a few years ago, a simulation of the Galileo Jupiter probe entry. And so it would be entirely possible to generate something like that for the Mars entry as well, perhaps with the limitations that Adam mentioned as we get closer to the surface.
Michelle, you were a little jumpy as well. I think we heard what you were saying, so thank you. Hopefully the everything. Oh, okay. Let's see. So we only got a couple of more minutes, and so. I thought I'd give an opportunity for all of the panelists to sort of give us our final thoughts. And my final thoughts is, wow, there's a lot of great work going on. And the three experts here are really moving forward the technology, and also get a real sense that we've got all this history from the robotic missions, and we're moving the technology forward. We understand the scaling problems. We're working on that. We've got demonstration flight tests getting us ready. We've got the Artemis program landing on the moon, which can provide lots of different data points, even though the environments are so different. And one thing that I think about when I think about the Artemis program is that just the operations part of it, having crew in a very dynamic environment, and building those systems and operating them and making the day-to-day choices, I think that's going to be really important as we move on to Mars. And at Mars, right, with the time delays, the crew will need to be much more independent from the ground. And so that's great that we're going to be able to practice that at the moon. But that's my thoughts. Why don't we go around the virtual room for some final thoughts?
We're going to go in speaking order. I'll go first then. Yeah, Tim, I think, I feel Mars is closer than ever now in terms of large missions. And I'm really excited to see all of the developments, the instruments and operations we can do at the moon. It's a really exciting proving ground. I'm excited to learn about Plume surface interaction and precision landing. Ashley and her team are going to be conducting some awesome ground tests that we've never seen the likes of before. So everything is moving in the right direction. We're very fortunate to have good support within NASA for advancing these technologies with a very large emphasis on modeling and simulation, which is going to be key for actually getting these systems matured and to flight. So on to Mars. I think Tim's having a little difficulty. Oh.
Can you hear me? Can you hear me?
Yes, we can.
Well, under the notion that you can, great. So I'd just briefly like to say the following, that for all of the technology development that we've discussed and the challenges that we appear to face technically, we have more technology in our hands today to put humans on the surface of Mars and return them safely to Earth than we did in the era of Apollo, when John F. Kennedy said we would put a man on the moon and return him to Earth by the end of the decade. So it is not at its ultimate foundation an issue of technology, but it is more an issue of political will and our place, the place of exploration in our world in a larger context.
Thanks, Adam. Ashley?
Well, that's going to be hard to top. We should let that one right out into the sunset. But no, I mean, we just echo back. It's been mentioned, and we've brought it up a number of times. We have this incredible heritage that draws at Mars. We reference back to the Viking era, and we say we have these Viking heritage systems, and that's where our breakpoints are being reached when you start talking about sending humans to the surface of Mars. A lot of the technologies that we've talked about today are also they're not new to the modern era. Many of them, though, were first conceptualized in that same era of innovation that led to the success of the Viking landers in 1976. So it's in that spirit that we pick up that torch and we continue pushing forward. There is so much work ongoing, and we're really seeing a really great collaboration between government, industry, academia, international partners, everyone coming together. And that's the only way we're going to successfully put blueprints on the surface of Mars. So, it's a really exciting time, and blueprints on Mars is within our grasp.
Great. Thanks. So thank you, Michelle, Adam, Ashley. I think that was a great conversation, and it really, sort of, I do this work day to day, but it's nice to kind of think, oh yes, we are close, and we are working hard, and we're going to get there. So thank you all, and I will hand it back to the conference organizers.
Thank you, guys. You guys got some love on the chat. One of their biggest thank yous was you took a lot of heavy duty information and made it so accessible. So there was great gratitude for that. Brilliant. And I think nothing excites all of us anymore here at Explore Mars than to think one day we will see people launch there and all of these exciting robotic missions preparing the way for humans there. So indeed, thank you to all of you. And now it is the end of day 3. That's how it is in COVID. You can't really know what day it is anymore. I see Chris and Ron looking like they're about to join me. We've got exciting things coming
Chris
up.
is just still a thing. We don't even know what's going on with Chris right now. I just messaged him and told him to turn his camera on.
Can you hear me?
We can hear you at least. Yeah, you
I don't know what's wrong. It says I have only stop camera. Let me see. Let me start. Nope, something's wrong with my camera. It's
change your camera. You need to change your camera. It's okay. See what had happened was.
That's all right. I've never seen a better camera view right now. This is my preferred snapshot right here. It's like.
Well, thank you, everybody. We are, again, grateful to all of you. Again, in this year that is 2020, anybody out there who wants to go into communications and develop, faster communications, we always have that speed of light thing to think about. But tomorrow coming up, let me just read you some highlights. You're going to hear from some of our very favorite people. Again, it's to be part of this incredible space industry family is just amazing. So tomorrow, coming up very first will be Dr. Tanya Harrison. She's going to be talking about the history of why Mars. And then up after her is Jim Garvin, who is the chief scientist at NASA Goddard. Then we've got a great planetary protection conversation with Matt Kaplan will be moderating that. It's Lisa Pratt, Alan Stern, and Mike Gold. And more to come in the afternoon. You'll be understanding we're about to celebrate the 20th anniversary on November 2nd of human exploration on the International Space Station, and how we can utilize the ISS to advance human exploration of Mars. And then my dear friend Vera Muliani will be talking about her Why Persevere moment. They'll also be able to see another chance to see those delightful students that I have had the privilege of working with for a while. We'll be able to talk about maintaining political momentum. And last but not least, we will end our conference with an entire panel talking about why we persevere. Dr. Cyan Proctor, James Garvin, your very own Ron Sparkman, Dr. Tanya Harris, and Sarah Lynn Mark. And my dear educator friend, Steve Sherman. So lots of great insights to end the day on. As always, we want to say thank you for being here with us, and we will see you bright and early and again in the morning. Martians unite, and it is our pleasure to bring you this content. We'll see you in the morning.